Bismillahirrahmanirrahim. Contents of our today's lecture are: today we will discuss ground fault protection of machine, and then we solve two solved examples in chapter number 7. So these are the contents of our today's lecture. Expected outcomes: at the end of the lecture, student will learn about the detection of ground fault in stator of rotating machines. Student will be able to learn about the impact of neutral grounding method on the stator ground fault protection of generators. So here we start discussion regarding the ground fault protection of the stator. In our last lecture, we have discussed in detail the phase fault of the stator. So this is the continuation of previous discussion, that the stator can have a line to ground fault, a line to line fault, or face to face fault, or a interturn fault. I had explained these terms in detail in our last lecture. Ground fault protection of generators depend on the grounding method, and here we can categorize grounding method into two categories. First is generator with grounded neutral. There is a connection between neutral and ground, and there could be further two categories of these grounding methods: solidly grounded neutral, or we have intentionally added an impedance between neutral and ground. Then there are further different methods of inserting that impedance. That could be a simple resistance, a reactor, or we can use this resistor or reactor on the secondary side of a grounding transformer. Second grounding method is generator with floating neutral. The behavior of generator in this condition, and if we had connected neutral through ground fault neutralizer, will be same, because ground fault neutralizer, that tuning coil, make the system virtually ungrounded. Mean behavior of system will be similar to an ungrounded system. So we can categorize that condition into this floating neutral condition. Now here I will show you different grounding method of the generator's neutral. The first one is direct earthing. When the neutral is directly connected to ground, here in case of the solidly grounded neutral, the line to ground fault can be even greater than three-phase fault at the terminal of the generator. This is considered as the most severe fault in power system. Generally, the most severe fault will be three-phase, but if neutral of a generator is solidly grounded, then single line to ground fault will become even greater than a three-phase fault at the terminal of the generator. So in this condition, no need to have any dedicated ground protection, because fault current through the phase protection will be sufficient. The relays are the method that we have used to detect the phase fault will be sufficient to detect the ground fault as well, because ground fault is sufficiently high here. But if we have connected neutral to ground through an impedance, that could be resistance, so that will be mainly for limiting the fault current. We have limited the level of short circuit fault current. Now a very quick and reliable protection can be provided if we provide a CT in the neutral circuit, connect a time delay or instantaneous overcurrent relay on the secondary side of this CT. So that is known as neutral connected CT and relay to provide protection against line to ground fault. When we discuss ground fault, obviously it means only the line to ground fault, because double line to ground fault is more severe than a line to line fault. So even phase relays can detect a double line to ground fault. So ground fault only refers to single line to ground fault. So in case of single line to ground fault, we can provide protection by detecting the current through the neutral circuit. Here, if grounding has been done with the help of a grounding transformer, then current is limited to a very small value. The fault current will range from 10 ampere to 35 ampere in the neutral circuit. So that is the purpose of grounding resistance through a grounding transformer. So we have inserted the resistance instead of directly inserting between neutral and ground, we have inserted through a grounding transformer. So in that condition, fault is detected by monitoring the voltage across that grounding resistance. Or second method to detect the fault in that mechanism is by monitoring the current on the secondary side of this grounding transformer. This grounding transformer is a step down transformer. Here this resistor is connected on the low voltage side, this one or this one. As voltage has reduced, current in the secondary circuit of this grounding transformer will be higher, much higher as compared to current in the primary circuit. So current in this circuit, this loop, will be much higher as compared to current here in the neutral circuit. Although we cannot use this neutral current for the detection of ground fault, but we have a sufficiently high current over here that could be used to detect the current fault with the help of monitoring of current. So overcurrent relay can be used here in this circuit. So we will discuss this method in further detail in upcoming slides, and we will also discuss the protection or detection of ground fault in ungrounded machines. So for generator with solidly grounded neutrals, differential protection that we had applied to detect a phase-to-phase fault or phase fault in the stator of the generator, that will be enough, because in case of solidly grounded neutral, fault current is too high and that could be easily detected by even the phase protection. In generators with the neutral grounding through impedance, differential relay may have problem in detection of fault. Now shortly with the help of an example, we'll discuss why differential relay may have a problem in detecting ground fault. So in that condition, when we have intentionally added an impedance to limit the fault current in case of single line to ground fault, a sensitive protection can be provided for a ground fault by using a CT and its connected instantaneous overcurrent relay or time delay overcurrent relay in the neutral circuit. So circuit is over here. So in this diagram you can see three phases of generator have been shown over here, and here we have next delta Y grounded transformer, which is known as GSU, generator step up transformer, that is connected immediately with the generator to step up the voltage to the transmission voltage level. Here we have done grounding through an impedance, neutral impedance, this one. So now we have inserted a CT and its connected relay in the neutral circuit to detect a ground fault if we had limited the ground fault current with the help of an added impedance in the neutral circuit. So now here we solve this example step by step and see how the grounding method impact the protection that we are going to deploy for the protection against ground fault. For this example, we have taken this generator and fault is at this location inside the zone of differential relay that we are using for the stator phase fault. And here in the neutral circuit, we have shown a resistance Rn to limit the fault current and added CT and its connected relay in the neutral circuit to detect the ground fault. It is given that this generator is rated at 125 MVA. Line to line voltage at the terminal of this generator is 15.5 kilovolt, that is the rated voltage of the machine. So sub-transient reactance, which is equal to its positive sequence as well as negative sequence reactance, is given as 0.2 per unit or 20%, and zero sequence reactance of the generator is given as 0.03 per unit or 3%. and based upon these rating, the rating of generator is same as we have seen in the previous example in last lecture. So a load current, which we will use as base current as well to convert the per unit current into actual value. Load current, which has been calculated by using the rating of generator, is 4656 ampere. Now according to this rated current, we have selected the CT ratio, which is same as we have selected in our last example, that is 5000 into 5. So obviously these two CTs are stepping down current by 1000 times, and CT ratio has been selected in such a way that during the normal steady state operation of the generator, secondary current of CT should not be more than rated secondary current, which is 5 ampere. So obviously against this rated current, we will get 4.66 ampere on the secondary side of the CTs during normal operation. So here for neutral connected CT, we have selected a CT ratio 100 into 5. So we arbitrarily selected this small CT ratio by assuming that the neutral is not carrying any current or very little current during normal operation because generator is operating in balance condition. So due to this reason, CT ratio can be as small as 100 into 5. Let's see the first case. In this first case, we have assumed that Rn, the grounding resistance, is equal to 0. Mean generator neutral is solidly grounded. So we know that in this condition fault current level will be too high. Let's do the calculation to find out the fault current. Here is the equation to calculate the fault current. IF is equal to the, in case of single line to ground fault, that will be equal to 3 times zero sequence fault current. So zero sequence fault current is pre-fault voltage divided by positive sequence reactance plus negative sequence reactance plus zero sequence reactance plus 3 times grounding resistance in per unit into I base to convert this current into ampere. So this is the formula to calculate the fault current. Now if we substitute the values of these reactances, voltage and base value and Rn, the fault current will be 32,484 ampere. Again we can compare at this point that in case of line three-phase fault that we have calculated in our last lecture, for the same generator three-phase fault at the terminal of the generator was about 23,000, and here single line to ground fault is 32,000 ampere. So obviously it is higher than even three-phase fault because neutral is solidly grounded. Now against this much high fault current, the current that we get here on the secondary side of these CTs, that would be 32.5 ampere. Obviously this current is passing through only one CT, only through this CT, then it will move into the ground and take this path here into ground back to the phase like this. So this fault current 32,484 is passing through the primary of this CT connected in the neutral of the generator. Okay, differential relay CTs and neutral CTs. So only one phase of a three-phase generator have been shown over here. Other two phases will be similar to this one. Okay, now normally the set value of our current differential will be from this range 0.2 ampere to 0.4 ampere. So that is the normal pickup value of simple overcurrent differential. We are not talking about the bias differential, percentage differential. So here we can see this 32.5 ampere which will flow towards the differential branch or differential relay is much higher than I set, that is 0.2 to 0.4. It means even this differential relay that we are using for phase fault detection can reliably and easily detect this ground fault, because ground fault current is even higher than the three-phase fault current. So no problem for this differential relay to detect this fault. And let's see what we are getting on the secondary side of this neutral connected CT. This one. So in the secondary circuit of neutral connected CT, we are getting 1624 ampere. That is too high current for any protection equipment to be connected on the CT secondary side. In order to reduce this current, we will have to use higher CT ratio. But question is, if our phase fault relay is detecting the fault properly and reliably, then why we are inserting any dedicated protection in the neutral circuit? No need to insert any dedicated protection over there. So conclusion here, in case of solidly grounded neutral, phase fault protection is sufficient for ground fault protection as well. Now let's see the second case. That is moderately high grounding impedance. Rn is equal to 1 ohm. We have inserted 1 ohm resistance in the neutral circuit. Then this resistance value in per unit will be the actual value divided by the base impedance based upon the rating of this generator, that is the voltage square divided by the power, MVA power. 15.5 square divided by 125, that will be Z base. 1 divided by Z base, per unit value of this resistance is 0.52 per unit. And here is a formula to calculate a single line to ground fault. By substituting the values here in this formula, here x1, x2 and x0, these are the reactances, r is the resistance. So here in the denominator, the sum of all these four values will be a complex number having a real part equal to 3 times of 0.52 plus the imaginary part sum of three reactances, positive, negative and zero sequence. So after substituting the value, the fault current is 8632 ampere. Look here, by just inserting 1 ohm resistor in the neutral circuit, current has been reduced by 4 times. Previously it was 32,000, now it is just 8,000. Okay, we are not interested in this angle, we are interested only in the magnitude of this fault current. So here on the secondary side of this city, we will get a secondary current 8.6 ampere. And if we compare this 8.6 ampere current with the setting of the relay, which is from 0.2 to 0.4 ampere, it is again sufficiently higher than this value. It means differential relay that we are using to provide protection against the stator phase fault can also detect ground fault, because in this condition fault current is still sufficiently higher than that. Let's see what is happening here in the neutral connected CT. On the secondary side of this CT, we are getting 432 ampere current. So now here, if we install an instantaneous overcurrent relay in the neutral circuit, instead of this time delay, here we use instantaneous 50N. 50 stand for instantaneous overcurrent relay. And set its pickup, I set equal to 50 ampere. That can provide a reliable and very quick protection against this line to ground fault. Now here conclusion is, although in case of moderately high grounding impedance, ground fault can be detected by a phase fault relay, but a neutral connected CT and an instantaneous overcurrent relay can provide a quick and reliable protection if we want. Otherwise, phase fault relay is also sufficient. Now the third case, when we are using very high grounding impedance, grounding resistance, this time we have inserted 10 ohm, that is 10 times higher than the previous value of grounding resistance. So per unit value of this resistance is 5.2 per unit. And if we substitute the value of reactances and 3 time of this grounding resistance in this equation, multiply with the I base, fault current will be 895 ampere. This is single line to ground fault current. So here this fault current will flow into ground at this point. So fault current is passing through the primary of this CT. So here on the secondary side of this current transformer, we will get a 0.895 ampere which will flow towards the differential branch, differential relay. Although I set is still less than this value, relay can detect this fault. But if this fault occurs through a grounding, a fault resistance, means if fault occurs here through an additional resistance like this, then fault current level will further reduce and differential relay, or you can say phase fault relay, may fail to detect this fault. Okay. Then the solution of this problem is, let's see what is happening over here in neutral connected CT. Here in neutral connected CT, we are getting 44.75 ampere in the secondary circuit. So if we use a time delay over current relay with a setting of I set will be equal to just 5 ampere. So this time delay over current relay will get a fault current which is sufficiently higher than its set value 5 ampere, at least 9 times or around 8 times. If fault occurs through additional resistance, even then we get sufficient value of current over here to be detected by this time delay over current relay in the neutral circuit. Now question is, a fault which was missed by the phase differential relay can be detected by a dedicated protection in the neutral circuit. Why it had happened in that way? Why the phase fault relay has failed and but the neutral connected dedicated CT and its relay has detected the fault reliably? The reason is CT ratio. CT ratio in the neutral circuit is as low as 100 into 5, but the CT ratio for phase differential relay is 5000 into 5, means it will transform 5000 ampere to the 5 ampere current, means stepping down the current by 1000 times, but neutral CT is just stepping down the current by 20 times. Reason for the selecting these CT ratios: for phase fault detection, the CTs inserted over there, they will carry a normal current of 4656 ampere during the normal operation. That's why CT ratio is too high, because it is carrying the normal current during the normal operation of generator. That very high CT ratio will make a low magnitude fault current insensitive. So relay, this differential relay would not be able to reliably detect a low magnitude fault and will become insensitive to those faults. But here the CT ratio in the neutral circuit is independent from this normal load current, because neutral does not carry any current during the balance operation of the power system, and it will carry only the leakage current or the third harmonic current, or you can say unbalancing current, zero sequence current, which will be negligible during the normal operation. But when fault occurs, single line to ground fault, we have sufficiently high current over here. So due to this reason, we can select the CT ratio as small as 100/5 to have a sufficiently higher value of current on the secondary side of the CT to be detected by a relay. So this was a statement that we have discussed previously. Now if I summarize over here, in case of solidly grounded neutral, no need to use any dedicated protection in the neutral circuit. Phase fault relay can easily detect the ground faults. In case of moderately high grounding impedance, the phase fault relay can detect a ground fault, but if we use a neutral connected CT and its secondary have secondary has an instantaneous overcurrent delay, we can provide very quick and reliable protection against ground fault. But in case of very high grounding resistance, where fault current has been limited to a very low value, phase fault relay may fail to detect this fault. But we can still provide a very sensitive protection by connecting a CT and its associated time delay overcurrent relay in the neutral circuit that we have seen here in this example. So this was the protection of generator against ground faults, and we have seen that grounding method has impact on the technique that we are using to detect the ground fault. What about the motors? Remember, small motors are operated in ungrounded condition, mean their neutral will be in floating condition, but large size motor may have their neutral connected to ground but through a high impedance to limit the fault current to a safe value, but their neutral will be grounded. So here we have two examples. Maybe we discuss those two examples in any next lecture if we get some time. So we will discuss then how to provide protection to motors against ground fault. Now we will discuss the protection of machine in case of neutral is floating or we have connected neutral to ground through ground fault neutralizer. Remember, if machine is not grounded, then the first ground fault does not result any current flow. Even in case of grounding through ground fault neutralizer, in case of line to ground fault, current will be negligibly small. So this situation does not require immediate tripping. We do not want to isolate our machine from the system in case of a line to ground fault if neutral is in floating condition. However, if another line to ground fault will occur in the presence of already existing line to ground fault, then that would become a phase to phase fault or a turn to turn fault. Meaning grounding was already there, another point has become grounded in the presence of already existing ground. So that could be a problematic situation because this condition can result in heavy current or magnetic unbalancing and does require a tripping. So due to this reason, detection of first ground fault is important. We want to detect the first ground fault and take appropriate action against that ground fault. In case of generator, so if a ground fault is detected and that is inside the winding, then in the upcoming scheduled shutdown of the generator, their problem will be addressed immediately. Okay. Here we'll discuss how to detect the ground fault in case of ungrounded machine. So the method that we use to detect a ground fault is with the help of the potential transformer. Three-phase VTs are used for that purpose. And majority of you have already performed an experiment to detect ground fault in ungrounded system in power system protection lab. That was experiment number 14, and you had used a three-phase VT where the primary of voltage transformer were Y connected with neutral was grounded and secondaries were connected in broken delta configuration. So primary winding connected in grounded Y configuration and the secondary winding connected in broken delta. Here you can see how the VTs are connected to detect a ground fault. The primaries are Y grounded and secondaries are connected in broken delta. So here this relay will be an hour voltage relay. 59 is standard designation number for our voltage relay. And in case of line to ground fault, 59, this our voltage relay would detect a zero sequence voltage, which is 3 times of total zero sequence voltage that will appear across these broken delta points. When everything is normal, the three phases of these voltage transformers here, the primaries, will carry equal voltages in magnitude and will also have a phase difference of 120 degree from each other. So this voltage transformer will step down that voltage here on the secondary side, and in this configuration we are adding those three voltages. For example, if this is a dotted end of the primaries, corresponding dotted end on the secondary side are here. Okay, the induced voltage on the secondary side by the transformer action will be in this polarity, plus minus, plus minus. This is instantaneous polarity. Okay. If we look here, by connecting the secondary side in this broken delta configuration, we are effectively adding these three voltages. The sum of three voltages which are equal in magnitude and displaced by 120 degree, that would be equal to 0. So that is a normal condition. Let's say a ground fault occurs in any of these phases. For example, here grounding has been done in this phase. You can see if I connect these two points together, there is a short circuit in parallel with this phase. So it means primary voltage across this VT will collapse to 0, and same is the case over here on the secondary side. Across this winding we get a 0 voltage. Now when we add these three voltages in which one is 0, then the sum of these three voltage is not going to be 0. That would become 3 times 0 sequence voltage mathematically. In this way a ground fault is detected. Although due to this grounding there will be no fault current, but these VTs can produce a 0 sequence voltage, and that could be detected with the help of an hour voltage relay to detect the grounding. So that indicates that grounding has been done. So attention is required to clear that ground fault. So anywhere in the power system, whether that is transmission line, generators, or any other part of the power system where system is ungrounded, grounding can be detected with the help of this method. The three-phase VTs where primaries are connected in Y grounded formation and secondaries in broken delta, and we will observe voltage across the broken delta. So there will be an other voltage that could appear across this over voltage relay, and that is the third harmonic voltage. Remember, the behavior of third harmonic and zero sequence is same, because zero sequence and third harmonic both are equal in magnitude as well as in phase in all the three phases. The only difference between third harmonic and zero sequence is the frequency. Zero sequence current and voltages will have the fundamental frequency, but the third harmonic and triplet harmonic will have a frequency that is at least 3 times higher than the fundamental. So next triplet harmonic will be, if even harmonics are there, that would be the 6, then 9, then 12, and so on. So these harmonics, their behavior is similar to the zero sequence. If we have a third harmonic component in the voltage, that would appear across this relay 59 even in the normal condition. So when you were performing this experiment in the lab, you had observed that when we remove all the capacitances that exist between line and ground, we get a voltage across this relay 59 over voltage relay. That was around 23 or 21, sometime 22 volt. So that was actually third harmonic voltage. Question is why that voltage was appearing here across these broken delta points when we have removed all the capacitances. In the presence of capacitance, there will be no such voltage. Remember that line to ground capacitances were providing path for the flow of third harmonic current, because due to higher frequency, the capacitive reactance will reduce for third harmonic as compared to fundamental. So third harmonic will get an easier path for the flow through those stray capacitances. Once we remove all those stray capacitances, then the only path for the flow of third harmonic current or the existence of third harmonic voltage is this VT. If we connect the three terminals to the ground through those stray capacitances, so third harmonic will take that capacitive path instead of passing through the three windings of this voltage transformer, because it is highly inductive. It gives very high impedance path for the flow of third harmonic current. So due to this reason we were getting zero voltage when all the stake capacitances were in service, and we get a voltage even in normal condition across this relay when all the stake capacitances, line to ground capacitances, were removed. So I hope you have got this question. So remember, the pickup setting of this relay should be set twice as the normal voltage that we may get across this our voltage relay. That will be due to third harmonic. Now we discuss the other methods that could be used to detect a ground fault if we cannot provide a CT in the neutral circuit, or we don't have any CT over there. So if neutral is not accessible, to insert a CT over there to have a sensitive protection for ground fault, we have alternate schemes. So first scheme is residually connected relay. Residually connected CTs mean CT secondaries are in Y connected, and the path between two neutral is known as residual path. The relay inserted over there which is observing the residual current. Residual current is the zero sequence current. That is known as residually connected relay. Here in this diagram you can see between this neutral point and this neutral point, this is a path which is known as residual path. Total current here will be neutral current, which is 3 times zero sequence current. Relay which is observing this current here, this 51G, is a residually connected relay. So we can use this relay to detect the ground fault. Okay, remember here for this relay it must be a time delay over current relay. We cannot use an instantaneous over current relay over there. Reason, because when we start a motor draw very high current, that is inrush current, and due to switching instant on the system, that current may have a DC component in it. So due to that reason, these three currents, phase A, phase B and phase C, their sum may not be equal to 0, and we may get a current over here even during the normal condition. Starting a motor is a normal condition. So that's why the operation of this relay should be delayed, so that it should wait for the motor to start, and then if current is there after that time, that is indication of a fault. So during the motor starting time, this relay will wait for that time, because current will be there in the residual part due to DC offset in the primary currents. So the relay that is connected in the residual of the CT secondary circuit, it sees a vector sum of secondary current of all the three phases, which is equal to the 3 times of zero sequence current or the neutral current. When motor is energized, a DC offset current flows in all the phases that cause current through residually connected relay. Therefore, instantaneous relay cannot be used here in this path. So alternate is a very inverse or short time induction relay, short time inverse. So these are the types of inverse characteristics, or its solid state or digital equivalent is required. Now problem with this type of protection is, again we are taking current from the phase connected CTs which has very high CT ratio. So in case of low magnitude of fault current, we may not be able to get sufficient value of zero sequence current so that relay could be operated on that current. So to solve this problem, alternate to this residually connected CT is a toroidal CT or flux summing CT. Here is the toroidal CT where all the three conductor has been passed through the core of this CT, and we have secondary across this core. So this secondary winding of toroidal CT will carry the current equivalent to the sum of the three current through these conductors. In balanced condition, the sum of three currents will be 0, and in case of line to ground fault, we get a sufficiently high sum, that is the 3 times of zero sequence current. Remember, this is the core, and here is the sheath over the conductor or the armor, that is a metallic covering around the cable to provide protection to the conductor of the cable from external stresses. So normally this sheath or armor is grounded. So due to this reason, make sure that the sheath is not passing through the core. Otherwise, the zero sequence current will also pass through the core of this flux summing city, and we get nothing at the output of, or very little current at the output of that toroidal city. If it is not possible to keep the sheath out of the core of this flux summing city, then we will have to cancel out that current by threading this grounding conductor back through the core, so that it will cancel out the current carried by this core. So here actually this armor around the cable was carrying a current here in this direction, flowing into this neutral circuit, and this conductor has been passed back through the core of this toroidal city to cancel out this total current. So now the net sum which is producing flux in this flux summing city is these three currents, IA plus IB plus IC plus the neutral current in the sheath, and then we have passed the connector back, so that will be plus minus I and neutral current, so that will be equal to 3 times of zero sequence current. Now we discuss the grounding method of generator that I have introduced at the start of this lecture, grounding through grounding transformer. Because when we insert our resistance in the neutral or reactor in the neutral circuit, normally that is to limit the fault current to a safe level. Safe level means which is safe to be interrupted by the circuit breaker. But sometimes grounding is done to reduce the fault current level to a very low value, that will be from just 10 to 35 ampere. So fault current has been reduced by this reactor or resistor to a very low value. In these applications, due to economic reasons, the most popular arrangement uses a distribution transformer and a resistance combination. If our goal is to limit the fault current to such a low level, then this is the method that we use. Instead of inserting the resistance or reactance of very high value directly between neutral and ground, we insert that resistance or reactance through a grounding transformer, and economically use of resistance in the secondary side of grounding transformer will be an economical method. Now we'll see how to select that transformer. The primary voltage rating of that distribution transformer that we insert between neutral and ground, that must be equal or greater than the line to neutral voltage of the generator. And the secondary voltage level, so these are the three standard secondary voltages: 120, 240 or 480. Secondary can be rated on any of these three voltages, but primary should be greater than the line to neutral voltage of the generator. So here in this diagram, an arrangement have been shown how the grounding will be done through grounding transformer. You can see different components of generator and the bus. We have a generator, its associated step up transformer, that is GSU, generator step up transformer, connected in delta by grounded configuration. Delta side will always be towards the generator, and then that generated power will be connected to the system through this transformer at transmission voltage level. Here the neutral of this generator is connected to ground through this grounding transformer. In case of a line to ground fault at the terminal of the generator, the line to neutral voltage, this voltage, would appear across the primary of this transformer, grounding transformer, in this polarity. When a line to ground fault occurs here at the terminal, so line to neutral voltage will be across the primary of this grounding transformer. Due to this reason, a rating of this primary winding should be equal or greater than the line to neutral voltages of generator. Next is, what should be the value of resistance to be inserted in the neutral circuit? There are two requirements for the selection of that resistance. So first criteria for the selection of that resistance, a secondary resistance selected so that in case of a line to ground fault at the terminal of the generator, the power dissipation in that resistance should be equal or greater than total capacitive reactive power dissipation in stray capacitances. So power dissipation in resistance should be equal to the reactive power that is dissipated in zero sequence capacitances or stray capacitances. So those stray capacitances are actually stray capacitance that exists between generator winding and ground. So that will be between winding and the core and between winding and the casing of the generator. Second will be the capacitance that exists between leads, which is used to connect the generator with the generator step up transformer. So there will be a capacitance between those conductor and ground. And third part of that capacitance is surge arrestor capacitance. Okay. Lightning arrestors are installed at the terminal of the generator. So third component will be that, and fourth will be transformer winding capacitance. So the second criteria, the current should be between these two limits. It should be greater than 10 ampere and not more than 35 ampere. So this is the lower and upper limit of fault current. So these two conditions should be satisfied simultaneously if possible. Otherwise, we will impose this limit of current if not possible to satisfy both conditions simultaneously. So this fault current 10 to 35 ampere, that is not sufficient to operate any phase fault relay or even any neutral connected relay, because 10 ampere fault current is nothing, 35 ampere fault current is nothing. So if we have connected a CT and then observing current on the secondary side of the CT, that will not be sufficient to operate a relay. So due to this reason, we have another method to provide protection, that is an over voltage relay connected across that grounding resistance in the secondary circuit of grounding transformer, where we get the full secondary voltage in case of a line to ground fault when fault occurs. So there was an experiment number, I think that was 10. So grounding of neutral of generator through grounding transformer. You have applied this protection and detected the ground fault with the help of an over voltage relay. So now we'll see the impedance that would reflect in the primary circuit. That will be based upon the transformer turn ratio. For example, if a transformer has voltage of 26 kilovolt terminal voltage line to line, so line to ground will become 15 kilovolt, and the distribution transformer that we have connected in the neutral circuit has a ratio 15 kilovolt to 40 volt, and we have inserted 1 ohm resistance in the secondary circuit. The primary resistance that would appear in the primary side of this distribution transformer will be 1 ohm multiplied by square of the transformer ratio. So that will be 3906 ohm. So if this much high resistance will appear in the neutral circuit, how much will be the fault current in case of line to ground fault? So resulting generator ground current will be the line to ground voltage divided by this impedance, that will be 3.84 ampere. Now here we solve the example number 2, that will be setting of this time delay over voltage relay across this grounding resistance over here. It is given that a generator of 12.5 MVA are 12,500 kVA. Rated voltage of this three-phase generator is 15.5 kilovolt. Set the relay 59N in the neutral circuit. So this is the task. Further data that is given for this system is the voltage ratio of this grounding transformer is 14.4 kilovolt to 480 volt. This is the transformer turn ratio that has been used in the neutral circuit. So it is given that the stray capacitance of generator winding is 0.22 microfarad per phase. Zero sequence capacitance of transformer winding, you can see that is the delta wind side of that generator step up transformer. So that stray capacitance is 0.1 microfarad per phase. And stray capacitance of lightning arrestor that has been installed, its location is incorrect. That would be on the terminal of this generator, but as this diagram has been taken from your textbook and by mistake it has been shown over there, this capacitance, stray capacitance, is given as 0.25 microfarad per phase. So there will be three lightning arrestor in three phases and location will be between generator and transformer. So now we are going to select the first resistance value. What should be the value of a resistance? Then we will select the power rating of this transformer. Third task will be to set the setting of this over voltage relay connected in the neutral circuit so that it could detect a fault. So the criteria for the selection of resistance: in case of line to ground fault, the power loss in this resistance should be greater than or equal to the total stray capacitance is reactive power loss. This is first criteria. Second criteria, in case of line to ground fault at the terminal of the generator, current should be in the range of 10 to 35 ampere. So these two conditions should be satisfied at the same time. So first let's see the first condition, that the power loss should be greater than total capacitive power loss in the stray capacitance. Here we are going to calculate the total stray capacitor loss. So reactive power in all the capacitances, stray capacitances, is equal to stray capacitances of transformer plus reactive power in stray capacitances of generator plus reactive power dissipated in the stray capacitance of lightning arrestor. And the formula to calculate the stray capacitance reactive power is phase voltage square divided by XC in that phase. So that will give us per phase reactive power dissipation in a stray capacitance. Okay, and if we convert into three phase, multiplied with 3. So let's substitute the values here in this equation. So this will become 3 into V phase square into 1 over XC transformer, 1 over capacitive reactance of generator, 1 over capacitive reactance of lightning arrestor. I have added all three of them together. So 3V phase square, that was common among all the three factors. That's why I have taken it common. Next, we know that capacitive reactance will be 1 over 2 pi Fc and its reciprocal will become 2 pi Fc. So that 2 pi Fc has been taken common, and this is the formula to calculate QC. That is 3 into V phase square into 2 pi F into stray capacitance of transformer plus stray capacitance of generator plus stray capacitance of lightning arrestor per phase. If we substitute the value of these capacitances from the diagram given as C transformer is 0.1 microfarad, C generator is 0.22 microfarad and C lightning arrestor is 0.25 microfarad, the total reactive power loss in stray capacitances was 51.63 kVAR, kilovolt ampere reactive. So it means in case of line to ground fault, the power resistive power loss should be equal or greater than this value of QC, which is 51.63 kVr. Now we can select the value of resistance very easily from this value, because we have the value of power, we know the voltage level, so we can use the formula to calculate the resistance to be inserted in the neutral circuit to satisfy this condition. But there is another condition, and that condition is the neutral current should be between 10 to 35 ampere. Let's see what will be the neutral current if we satisfy only this criteria, that power loss is equal to 51.63 kilowatt. Here, by using this equation, P loss is equal to V phase multiplied by neutral current. That is a formula we have solved it for neutral current. So by substituting the value of P loss equal to 51.63 and V phase equal to 15.5 kilovolt divided by under root 3, that is equal to 5.77 ampere. It means if we satisfy only this criteria, that P loss should be greater than Q loss, neutral current should be equal will be equal to 5.77 ampere. But remember, we need a current minimum value of current equal to 10 ampere. So that's why we will select the neutral current equal to 10 ampere. Okay, that is the lower limit of that range. Okay, according to that neutral current, the power loss in that resistance will become 90 kilowatt, and it has been calculated by multiplying this neutral current with the line to neutral voltages, phase voltages. So that is the power loss, and which is obviously greater than the QC. It is satisfying that equation, that P loss should be greater than QC. So that is our selection of neutral current. Now, what should be the rating of this power transformer? Because this much power will be dissipated. Power of this transformer is now to be calculated. Remember, this much power will be transferred through this transformer only when fault occurs. Mean transformer should be capable to handle this much power for short duration. So we will have to select a transformer which could carry up to 90 kilowatt for short duration. Remember, distribution transformers here that are the pole mounted transformer. These transformers can be overloaded beyond their rating up to 20% for a short duration, and that duration will be in few minutes. So it means if we divide this 90 kilowatt with 1.2, then we will get the power rating of this transformer, which is 75 kVA. So this transformer can be overloaded up to 90 kilowatt for short duration. So that is the method to determine the rating of this power transformer. Next is the calculation of resistance. Now we have all the data. We want to limit the fault current to 10 ampere. We have the system line to neutral voltages. Then the resistance to be inserted between neutral and this ground, that is Rn. That prime over that Rn describes that is a resistance to be inserted directly between neutral and ground, that is 895 ohm. We phase our In. Here, this is the resistance. But we want to insert this resistance on the secondary side of this distribution transformer, which has the voltage ratio 14.4 kilovolt to 480 volt. So we will have to transfer this Rn on the secondary side of this transformer. So that will become Rn is equal to Rn prime over A square. This Rg prime is actually same as Rn prime. So that is equal to 1 ohm. So what is this A? A will be 14.4 kilovolt divided by 480. That is A, transformer turn ratio. Here is the value of Rn, 1 ohm. Now resistance has been selected. Next thing is set the relay 59N. The our voltage relay that we had installed over here across this resistance. It is given that in the statement of the question that this generator is producing a voltage which can have a third harmonic component up to 3% of the rated voltage, and we know that zero third harmonic, its behavior is similar to that zero sequence. It means that current will flow through this neutral path, and when this current will flow through this neutral path, it will produce a voltage, and relay setting should be set higher than that voltage that exists in normal condition. Now V3 is a third harmonic of the voltage will is equal to 3% of line to neutral voltage. Line to neutral voltage is 15.5 kilovolt divided by under root 3, and our answer is 268 volt. Now in order to find out the voltage that will appear across that Rn even in normal condition, here I will draw the diagram in front of you. This is actual diagram, the three phases of the generator, and here we have the stray capacitances of the generator, and its value was 0.22 microfarad per phase. Similarly will be in other three phases, here as well as over here. Next come the lightning arrestor or surge arrestor. The three capacitances of surge arrestor, because surge arrestor have been installed in all three phases. So these are the three capacitances of surge arrestor, and its value is 0.25 microfarad. And next was the three capacitances of transformer winding, and its value is 0.1 microfarad. Here in the neutral circuit we have inserted a resistance that has value 895 ohm, because insertion of 1 ohm resistance on the secondary side of a grounding transformer is equivalent to inserting this 895 ohm directly between neutral and ground. Okay, now here I am just discussing the path for the flow of third harmonic current and voltage. How much voltage will appear here across this resistance due to this third harmonic voltage. Remember, third harmonic voltage will be same in magnitude and in phase in all the three phases. So that is 268 over here in this phase, here in this phase, and in this phase. So we can combine these three sources together in parallel like this, because their voltage level is same and their phase angle is same. We can combine these three terminals together, so that will become a single equivalent source having voltage 268. So next, when I have combined these three terminals together, what had happened to these stray capacitances? All the three stray capacitances in all three phases have become in parallel, and the stray capacitance of generator winding, stray capacitance of lightning arrestor, and stray capacitance of the transformer, that will be in parallel with each other as well. So we know that the parallel capacitances get added directly into each other. So what will be the total stray capacitances after combining all of them together? Here the stray capacitance of generator winding, when all the three combine together, that is 0.66 microfarad. Then the stray capacitance of lightning arrestor, that will become 0.75 microfarad per now it is total all the three phases. Then the stray capacitance of generator, that will become, this is a transformer, that will become 0.3 microfarad. Okay, now if I combine these two capacitances together and combine with this 895 5 ohm resistance. Net equivalent circuit will be something like this. We have a 3-phase voltage source in series with the capacitance, net capacitance of all the three, plus this grounding neutral resistance, that is 895. Now if we convert these total capacitances, that will become 1.71. If we add all these together, that will become 1.71 microfarad, and convert into reactance, that would become minus j 517. So remember, in order to convert capacitance into reactance, use frequency that is 3 times a fundamental. So formula will be 1 over 2 pi into f will be 180 into c, that is 1.71 microfarad, and that is equal to minus j 517 ohm. So here this voltage is 268. Now we can apply simple voltage division rule to find out the voltage across this neutral resistance. Okay, that will be the voltage that appear across the primary of grounding transformer. Let me write that formula here and then I will use the result directly. V in the neutral circuit, that is the third harmonic, will be equal to 895 plus the total impedance of this branch, that is 895 minus j 517 multiplied by total source voltage 268, and this value of third harmonic neutral voltage is 232 volt. Okay, when this voltage referred on the secondary side of that grounding transformer, so multiplied with the ratio, that is 480 over 14,400 volt, and this will result in 7.73 volt. Okay, now this is the voltage that is continuously available across that grounding resistance on the secondary side of that grounding transformer, and this is the voltage which is available to the relay all the time. So relay setting should be equal to twice of this voltage, so safety margin will be 100% above this value. So V set will be equal to twice of this, we can easily set to 16 volt. So that is the setting of voltage relay. So this is the criteria how we select the voltage relay. In the lab we have done this selection by assuming that we want to provide protection up to 90% of winding, only 10% will be unprotected. So but the actual criteria for the selection of the setting is in this manner. Let's end up this lecture over here.